All right, let's dive into a topic that, at first glance, can look pretty messy: heterogeneous equilibria. But what if I told you the secret to mastering these reactions wasn't about crunching more numbers, but about knowing what not to calculate? It really is the art of knowing what to ignore. So let's get into it. So here's the big question, right? You've got a reaction going. There are solids, there are liquids, there are gases, all jumbled together in one container. How in the world do you figure out the equilibrium? It seems super complicated, but it turns out chemists have this incredibly simple, almost elegant trick that makes it all fall into place.
Okay, so before we can solve this puzzle, we first need to get a really clear picture of the board we're playing on. We have to define exactly what kind of system we're even talking about.
And that brings us to our big term for the day: heterogeneous equilibrium. Now, heterogeneous sounds fancy, but it just means made of different parts. So we're talking about a chemical reaction that has reached a state of balance, but the stuff inside is in different physical states. You might have a solid reacting with a gas, or a liquid with something dissolved in water.
And this visual here really nails the difference. Over on the left, you see a homogeneous system. Everything's in the same phase, all mixed together perfectly, like sugar dissolved in your coffee. But on the right, well, that's where we're living today. These are the multi-phase systems. Think about ice melting in a glass of water. That's a solid and a liquid in equilibrium. That's what we're here to figure out.
All right, we've set the stage. We know what the problem is. Now for the solution. I promised you a secret, a kind of golden rule that honestly just makes all the tricky stuff disappear.
And here it is. This is the game changer. When you're writing out that equilibrium expression, the K value, you completely, totally ignore anything that's a pure solid or a pure liquid. You literally just pretend they're not there. Now you're probably asking, why? How can we just do that? We'll get to the why in a second, but for now, just know that this is the rule.
Okay, let's put this rule to the test with a real example. We've got solid calcium carbonate breaking down into solid calcium oxide and carbon dioxide gas. Now normally, the expression would have all three chemicals in it. But we apply our golden rule, we ignore the solid calcium carbonate, and we ignore the solid calcium oxide. So, what's left? The equilibrium constant, K, is simply the concentration of the CO2 gas. That's it. All that other stuff just vanishes from the equation. So why? Why do we get to just ignore them? It kind of feels like cheating, right? But it's not magic, I promise. It's actually based on a really fundamental physical principle. Let's peel back the curtain on this constant concentration secret. This is such a great way to think about it. Imagine you have a solid block. Its concentration is basically its density, right? Mass divided by volume. Now what happens if you add more of the solid? Well, the mass goes up, but the volume goes up by the exact same proportion. So that ratio, the concentration, it stays perfectly constant. It doesn't change. Unlike a gas, you can't squish it to make it more concentrated. It's fixed. So chemists just absorb that constant value right into the equilibrium constant, K. And if you need a quick and dirty summary, this table is basically your best friend. It puts it all in one place. Pure solids and pure liquids, their concentration is constant, so they are excluded from the K expression. Out they go. Gases and things dissolved in water, or aqueous solutions, their concentrations can change, so they are absolutely included. This is the simple check you can do on any reaction you see.
Okay, we know the rule, and we know why the rule works. So now, for the main event. Let's roll up our sleeves and actually solve one of these problems from beginning to end.
All right, here's the problem we're going to tackle. We've got carbon dioxide gas reacting with solid carbon to make carbon monoxide gas. We're told the Kp value is 3.0. We're starting with 0.48 bar of CO2 and no CO at all. Our goal? Find the final pressures of both gases once everything settles down into equilibrium.
And to solve this, we're going to use the chemist's secret weapon, the ICE table. That stands for initial, change, and equilibrium. So we fill in what we know. Initially, we have 0.48 bar of CO2 and 0 CO. The change is what we're solving for, so we call it X. So CO2 goes down by X, and CO goes up by 2X because of the balanced equation. But look at that middle column for solid carbon. It's completely grayed out. It's ignored. It's there, but it doesn't get to play in our math.
Okay, next step. We write out our Kp expression. Remember, it's always products over reactants. So it's the pressure of CO squared divided by the pressure of CO2. And of course, we ignore the solid carbon. Why? Because it's a solid. Then we just take those values from the E row of our ICE table and plug them right into the equation. So 3.0 equals 2x squared,
all over 0.48 minus x. And would you look at that, we've got ourselves a good old quadratic equation. Now don't worry, we just need to do a little bit of algebra to get it into that standard format. Once we have that, we can use the quadratic formula to solve for x. It'll give us two possible answers, but one of them is negative. And since we can't have a negative pressure, we know that's not the right one. So we take the positive value, which turns out to be 0.33.
All right, we've got our x. Now for the fun part, plugging it back in to get our final answers. The final pressure of CO2 is what we started with, 0.48 minus our x, 0.33, which gives us 0.15 bar. And the final pressure of CO is 2 times x, so 2 times 0.33, which is 0.66 bar. And there you have it. That's the state of our system at equilibrium. We solved it.
So we've gone through the theory, we've done a full problem. Let's wrap this all up by boiling everything we've learned down into 3 simple, powerful pillars to help you master this for good.
Pillar number 1, the phase rule. This is the big one, right? Always, always exclude pure solids and pure liquids from your equilibrium expression. Pillar 2, the unit standard. Just remember that K values don't have units. They're dimensionless. And finally, pillar 3, ice table discipline. The second you see a solid or liquid in your reaction, just get in the habit of crossing out its column on your ice table. These 3 pillars will always guide you to the right answer. And that kind of leaves us with a cool thought to end on. We've just seen how a huge, complicated-looking problem can become simple just by knowing what to ignore. So it makes you wonder, what other big, messy problems in science, or anywhere really, are just waiting for us to find that one simple, powerful rule that makes it all click? Thanks for joining me for this explainer.